Hello again. Okay, so this afternoon we really have two major sessions. One, what are we going to measure and how? And two, and what should we do with the data? That perhaps puts it backwards, but I figured that the people talking about data would be sufficiently entertaining that you'd want to leave for your wine promptly. Sorry, Jen. And I just wanted to point out that at the end of the day, and I'll try and say it again then, this room will be closed up and everything should be taken out so that it can be cleaned properly. We will be having our reception and meal upstairs in this building. And so you can migrate out of the room and take everything you have with you. If you are really concerned about security aspects or something, talk to us. There may be a way to lock things up, but it'd be easier if you just kept it with you in your own control. So, again, just to remind you, we will be handing around microphones again, and I really appreciate the work people put into using them this morning. Thank you very much. So, as I said, the goal here is to try and come up with some concrete developments of a regional observing network. And I'm going to talk a little bit about what I think we should measure. And this is based on my own prejudices and on prejudices that have been substantially formed by extensive discussions at these meetings. The real concern that I think we're going to have to come back to over and over is the distinction that Jan noted this morning about making measurements of what had been referred to somewhat metaphorically as weather quality and climate quality. The use of the word quality simply implying they're adequate for a particular purpose, and if the purpose is to see long-term changes in things that are varying slowly, sadly, you need very, very good quality, very, very low uncertainty to your data. On the other hand, if the goal is to characterize a local environment in regard to the CO2 chemistry at the sort of level we think really might matter to organisms growing there, and characterize the variability that exists in that location, then that is perhaps the weather quality of this. And I'm going to focus in my presentation on thinking about making measurements that are for this second usage. The measurements for the first have been extensively discussed by scientists looking really to ask the question, how much of the anthropogenic CO2 that's generated is really ending up in the oceans, and how is it distributed around in the oceans? And a lot of work has gone into saying, how can we make those measurements sufficiently well that we can do this? And we have, I think, a working knowledge of how to do that, and the message I would give is that it's expensive on a per measurement basis, particularly if you include the costs of training the people adequately to be able to do this consistently. And if you don't include those costs, you're fooling yourself. So really, my focus on the weather level is because I think that that's one that has been given very short shrift to date. That on the whole, the approach has been, we know how to measure CO2 in the oceans. Go and get Dixon's handbook, and you go, no way. This really looks like a lot of trouble. And the answer is, yeah, and it is. Those of you that had the opportunity to go with Guy and look at my lab earlier would get a chance to see the kind of trouble that it can be. So we're here somewhat in terra incognita because there are no clear statements of how good is the right level for this, what equipment you should buy, how you should use it. So I'm going to give you a somewhat personal flavor of this that, as I said, is substantially influenced by discussions that we've had at these meetings, and then make some rather bold recommendations at the end, and then we have an opportunity to discuss that more intently. But bear in mind that one of the goals of our discussion has to start going, okay, either this absolutely is not where we want to go, stop it dead now and go somewhere else, or if this is how we want to go, what's the next step? Not just saying we ought to do this, but why aren't we doing it already? And I have my own thoughts about that, but this is in some level a consensus-building exercise, and in others really very much taking advantage of the huge community of expertise and knowledge that's here to come up with the clear statements and thoughts about what we have to do. Because the real hard part is going to be doing it, and that will involve both people's time and trouble and people struggling to get the resources required to achieve it. So my proposed goal, and this simplifies down from a lot of the discussions we were having this morning, has been that an observing capacity would provide a description of the local seawater composition that was adequate to inform co-located biological studies, and which, when taken together with measurements from other locations, could form a picture of the regional variability in this. You would need some uniformity in how you ascertain the quality of these measurements, but they probably don't have to be of identical quality, rather, I think, of known quality, and you will need a data management structure to ensure availability. And the second half of the afternoon will be about that second aspect. So this is a somewhat narrower goal than the broad range of possibilities. And I think there are two main problems that come up. We have to recognize that there's a wide variety of potential contributors to a CCAN observing network, and that choosing how we do this in a way that limits that unnecessarily would be a problem. This is a careful use of the English language, such as in "a gentleman is never unknowingly rude." This doesn't preclude rudeness, merely suggests that you should know when you are being rude. In the same way, we need to know if there are people we wish to exclude, and we want to have a particular reason for it. It shouldn't be something that we're doing unknowingly. The other real complexity, which probably doesn't resolve in a very clear fashion, is to recognize that there's a variety of ways in which you could get data of appropriate quality. And therefore we have to decide, do we want to say, you only do it this way? Or can we think that in a way that opens it up to a larger group of people? Because one of the restrictions, of course, is people having the adequate training, experience, and instrumentation to make particular measurements. Is it desirable to restrict what we measure and therefore recognize that we necessarily have to worry about that, or can we broaden it? So we should be discussing those aspects. Well, under this, here perhaps is the ones many of us, or a number of us, are most familiar with. I've put academic in inverted commas to imply both the nature of the laboratory and perhaps the mental attitudes to thinking about this. These laboratories specialize in making CO2 measurements, have done already for some time, for varying reasons. They have significant experience. As I pointed out, at present, the majority of such laboratories, perhaps all, have been focused on, for want of a better phrase, open ocean measurements. And open ocean measurements are looking for climate quality CO2 measurements, that is, measurements with low uncertainty. And thus, at some level, the costs, although clearly a significant piece of this, have not been the first concern. The first concern is, can you make these measurements well enough to do what you wish? I'm suggesting that there are other contributors, and perhaps the major contributor that we at CCAN should be thinking about are ones that I would comment as laboratories who, in principle, have the capacity to make these measurements, but need advice or training. So, what does that little phrase, in principle, mean? I have individuals in my laboratory that can, in principle, make these measurements with advice and training, but some of them continually fail to do so. So it's not that everybody or anywhere could necessarily do this. My point here is really to point out that there are really two reasons to fall into this category in my mind. One is those laboratories that have their own reason for wanting to establish this capability. They might be academic laboratories who actually normally study organisms, but really feel they want to measure CO2 sufficiently well to make sense of the experiments and studies that they're doing. They could be analytical laboratories that actually make measurements of many, many other parameters, but have never yet even thought about making CO2 measurement parameters for ocean acidification related purposes, maybe water hardness and pH, but not really measurements of the kind that people thinking about the implications for aragonite saturation state might be concerned with. They're very used to having trained analytical chemists, to having people maintaining equipment, to worrying about the quality control of the laboratory. But they don't actually have this equipment today, and they don't have people trained to use it today. But in principle, they could. So those, to my mind, are different categories. Ones are really analytical laboratories that could adopt these measurements, but the others are research and other laboratories that say, you know, this is sufficiently important to us that we need to learn how to do this. But we need to think how well we learn how to do it, because there's a clear resource implication if we, at a certain level, it costs a certain amount. To get to be one of the very best CO2 measuring labs, it costs a lot more. And realistically, we have no need for that extra level of data quality, but we do really need to know how good the data are that we actually measure. And then, finally, there are bound to be others. One of the examples given on a map that Dick showed earlier was the Seattle Aquarium. They probably are not an academic CO2 measurement laboratory. They perhaps fall into that second category, but I would say they're probably in a third category. They're really looking to have measurements that they can use as part of outreach programs, as a way of showing to the public what's going on, maybe as a way of, and it could be that internally they're using this information for information about their own seawater in their own tanks. That's not the impression I've had in conversations I've heard before. But you can see that there's people that would still want to make competent CO2 measurements, but really don't quite fall into those previous categories. My own opinion, and one I think that a number of us have already expressed, is that it's that middle category that probably has the largest potential benefit in understanding how we might make people like that able to make CO2 measurements appropriately to contribute to a network of observations along the US West Coast. Now, as I said also, there's a wide variety of ways that data of appropriate quality could be obtained. We had this conversation briefly in this morning's discussion, and it's come up at our first meeting. It came up at the discussions in Seattle at the meeting that was held at the University of Washington. If you were to say, how well do you need CO2 measurements made? How might you choose to do that? Because the traditional statement, and had we but willed enough in time, I could explain to you the mathematics underlying it, is that if you measure two separate parameters of a seawater sample, two separate CO2 parameters, then usually you can infer all the other aspects of the CO2. That is, if you knew what the pH was and what the total dissolved inorganic carbon was, you could immediately use equilibrium relationships to calculate the PCO2 or the aragonite saturation state or the alkalinity. Now, some of these require other assumptions and information, which this is neither the time nor place really to discuss extensively, but the key feature is this requirement for two. What that really means is that one is not enough. Not just a lonely number, but inadequate as well. So measuring pH alone does not allow you to describe the CO2 system. Measuring PCO2 alone. This is a pity because you can actually buy instruments that measure PCO2 and sort of buy instruments that measure pH. Well, maybe I should buy instruments that sort of measure pH. But you'd have to have both to have a sensible description of the system. I've written this a little bit more elaborately because I added the word "and" here rather than implying that if you did that, that this would enable a complete description. I did that because there are colleagues of ours that are working out ways to measure carbonate ion concentration directly. If you did that, in principle, you could measure aragonite saturation state with one parameter. Of course, you wouldn't then have a complete description, and we had the discussion this morning about pointing out that, guys, if you're not a shellfish, maybe you don't care about aragonite saturation state if you don't have calcium carbonate as part of your exoskeleton. On the other hand, perhaps you do care about pH or PCO2. So it's that complete description that's really the important part. The harder part is to say, well, how well do we need this complete description? And here we came back to my original comment, which was adequate to inform co-located biological studies. Now, as I'm not a biologist, I'm undoubtedly going to start trampling on more toes here, but I would make the comment that probably you don't need it really well You need it so that it's clear that it's different here from what it was there. And at the moment, the experiments that I've looked at and read about in the scientific literature that look at biological responses to CO2 levels in seawater do not suggest to me that they are very sensitive to very small differences. Now, I know that need not be true. I will malign my wife here briefly. We live here in Southern California in a house that has both heating and air conditioning available on this switch in the wall. My wife, when it drops below 69, will be wanting to look for the heater. When it goes above 70, and she will walk to that switch, and I'll go, how does she know? And I'll walk to it too, to look at the display. And sure enough, there's this clear built-in system that is choosing an optimal temperature range, much to the enjoyment of our local gas and electric company and the chagrin of the people that pay the bills. Now, most organisms are not quite that sensitive to such small changes. And I'm going to make the case that that's probably true for CO2. Now, as I said, you can use any two or more, and mathematically, they should all be completely equivalent. And that's true. But in practice, that's not quite the case, because every one of these, the things you can measure, is an experimental quantity with an associated uncertainty. Even the equilibrium constants that you use for the calculations, or the estimates of how much boron there would be in seawater if you needed to correct for the alkalinity contribution due to boron, are all measured quantities with an uncertainty. These propagate through, and it becomes a rather elaborate arithmetic problem. There are simple calculators that allow you to do the calculation. There are, as yet, no calculators that allow you to figure out how badly you did it. There's a variety of other complications. These are all true, and these all really matter for climate level understanding of the CO2 system. What you're going to see shortly is I don't think they matter anywhere near as much once you say, I need it good enough, but let's not spend more money on making it too much better. A really ugly slide. I should have had more time in my planning to do this well. Okay. If we're looking for this uncertainty of plus or minus 0.2 in aragonite saturation state. Now, just to refresh your minds, for those of you who don't automatically think in your sleep of aragonite saturation states, it's essentially the ratio between how much carbonate ion is there in your solution relative to the amount you think would be there if it were at equilibrium with this hypothetical calcium carbonate mineral, aragonite. I say hypothetical because that's a chemical property and not probably really relevant to exactly the forms and the ways that biology are dealing with it. But it's still a description of the seawater, whether or not the actual number is useful to a biologist. So, first, the composition of seawater that gives an aragonite saturation state of about 2.2 is here. Of about 1 is here. I kept the alkalinity the same because I'm talking the simple view of ocean acidification that you've only added CO2 to the water. We've had discussions this morning that point out there are numerous other ways of modifying the composition of seawater which would make these things a little more complicated. But the idea I'm going to get across here, I hope, stays roughly the same. Now, one thing that's awkward is that what I've calculated here are how well these would have to be measured individually if the other measurement you made was perfect. So if you were working with alkalinity and total carbon, or even total carbon and pH, and you want to get this plus or minus 0.2, these are the kinds of uncertainties you're looking at. Now, the chance that one of your numbers is perfect and the other one isn't is small. Probably both of them are going to be imperfect. So these are kind of maximum values of what you might need. But those of you that work regularly in open ocean seawater chemistry, you look at those numbers and go, that bad? No. Because these are large numbers by comparison with the care that the open ocean seawater people have gone towards doing this. To give you an idea, in open ocean seawater, which kind of looks like this at the surface, we're doing this probably plus or minus 2. Plus or minus 2? I don't know. I think 0.01, 0.02, but others say 0.003. This one, probably plus or minus 3. So these are easily realizable numbers with the best available techniques. The question really is, are they still very realizable with more realistic techniques for most laboratories to adopt? The red piece on this investigates the particular pair that might be of interest, and we'll see in a moment quite why, pH and PCO2, because there, this number is, at this higher pH, fairly sensitive to the pH, not so sensitive to the PCO2. By the time you drop down to this level, yeah, it's really not that sensitive to the PCO2 and not unduly sensitive to the pH. That's the difficulty with this system, that any number that comes to your mind for a particular conditions doesn't apply perfectly for other conditions. And that's something we're going to have to get in the way of thinking about, because mostly our frame of reference has been judged with our ability to make these open ocean seawater samples, which are quite a narrow range of conditions, and usually a lot of focus has been on alkalinity and total carbon. Now, why? Well, I'm just going to list here and discuss quickly what I see as the advantages and disadvantages of making these measurements. Total carbon is the total amount of inorganic carbon system compounds there. These are unionized CO2, bicarbonate, carbonate, added together. Easy way to get it is to acidify the sample and extract all the CO2 that's produced and measure it. In fact, most of today's methods take that approach. If you got it in terms of moles per kilogram of solution, it doesn't change with temperature and pressure. That is, the relative proportions of all these species changes, but the total doesn't. So it's really quite easy to think about why, if it changed in your measurement, you can now think it's got to be a process that added CO2 to the water if it increased, or took it away if it decreased. For pH, real advantage, there are autonomous systems available. I put here master variable question mark. A lot of discussion of how processes are affected by changes in acid-base chemistry have been represented as changes in pH. People think of it, and even talked about it in the analytical chemical literature, as a master variable. One could discuss whether it really is a master variable or really it's just an indicator variable of what is happening to a large variety of things. But anyway, a lot of things talk about pH, and so if you actually measured it, you too can join the club and talk about it. PCO2, real benefit, autonomous systems are available. my own opinion is, as you can guess, that's the only benefit. Because I'm not sure quite what to make of it. Alkalinity, temperature, pressure, often possible to interpret changes. Total carbon, unambiguous interpretation. But alkalinity, not necessarily so straightforward. Disadvantages. Well, one of the most striking disadvantages for many of these is that if you gain or lose CO2, the number will change. So if you're collecting a sample, you have to collect it reasonably carefully so that you don't gain or lose CO2. How do you gain CO2? Well, if it's more in the atmosphere than there is in your sample, that's one way. But the most common way is that there are microorganisms that will decompose organic material in your sample and make more CO2. So we usually handle that by putting in something noxious like mercuric chloride to slow them down. So disadvantages. So I look through this and I go, you know, I'm still at stage 1. There are 4 things you could measure and you need 2. Why would you choose any particular 2? The temperature and pressure independent pair have real advantages where you're taking samples from the deep ocean and you're looking, and that because of this possible to interpret changes, you're looking to understand processes purely in terms of those changes. They're a bit cumbersome to measure. They don't have the phrase autonomous systems available there. So let's just go through a couple of these just to give you an idea of the kind of things that are in my mind as I think about this. First, total carbon. There's a couple of systems that you could buy. You can find the website, send the money, they'll send you the equipment. In actual fact, if you go to one of the companies, they'll send the person that built the equipment along with it to set it up in your lab and show you quickly how to use it. Now, advantages. This one, faster sample throughput, less waste disposal, less warm-up time, smaller samples. Sounds great. Disadvantages. Lower reproducibility, calibration not very stable, not been adequately tested. This one. Great reproducibility, calibration well tested, but slow, hazardous waste disposal, significant times you're not actually using the instrument. Anything perfect yet? No, no. But the one you think could be better, maybe that one. pH. Equipment cost is what usually gets people for pH. They go, I can buy a pH meter for, and then depending upon their view of what they're trying to measure, it varies between, $80 and $1,800. But relatively cheap. If you go the full whack of actually having the $1,800 instrument, you probably should also worry about what temperature you're measuring pH at. Because this is the problem. If you have a sample of seawater and you change its temperature, even though you didn't gain or lose any CO2 from that sample, the pH is going to change. It's easy to use, but needs regular recalibration. Uncertainty? I think it's around there. Limited availability of reference materials. Now, there's another way of doing it. I apologize, it's squeezed in wrong. Indicator and spectrophotometer. Well, significantly more expensive. Can be automated. Marginally better uncertainty, but it requires an indicator dye. The basic approach here is if you put a species in your water where the acid and base forms have different colors, by looking at the color, you can tell what the pH is. Those of you fortunate enough, A, to have a swimming pool, and B, to want to use it often enough that you have to keep it in good condition, will be aware of this technique. If you use a spectrophotometer to look at the pH, it costs more, but the pH precision is pretty good. However, getting pure dye is not so straightforward. At this time, I only know of 2 labs in the world that actually make this for their own research purposes and which they can be persuaded to share with friends. This is not what I refer to as a sustainable commercial system yet. The CFET system, based on the Honeywell Durafet, this is now marketed by Atlantic, could also be used. It's really an electrometric pH cell. The real benefit is it too probably needs regular recalibration, but instead of once an hour, they're hoping that once every few months to a year would work. Hoping, I say, because there probably hasn't been enough work done to show that it always works well. PCO2, well, equipment costs I've listed here are for commercially available systems. I think it's fair to say in all cases here, there are commercially available systems and then there are ones that people assembled in their own laboratory, which necessarily were much cheaper because they forgot how much time they spent assembling it and didn't actually charge that at minimum wage or at least some sensible number. The real problem here with PCO2, what you're doing is saying, I'm going to make another sample that's in equilibrium with my seawater. I'm going to measure some property of that sample that tells me how much unionized CO2 there was in the seawater. And it's an equilibrator, and it depends on the design of the equilibrator. Almost all of these, the quality depends on, but, you know, realistically, you can probably get a few percent very easily. If we went back to those of you that were photographic memories, where we were saying that probably if you had this within 5 or 6%, you were okay. Could be done. So, uncertainties. Well, I put this table together. It really just reflects a few thoughts in my mind about what's involved. This was for a separate purpose, so it doesn't tell you everything you might want to know, I fear. But in a state-of-the-art laboratory, and I would consider our own lab like that, you can do quite well with these measurements. If we go to sea and try and make the measurements, we can still do quite well, but things never work quite as well. We've tried other techniques in our lab, and if we're calibrating them and doing careful quality control, we kind of fall in these ranges. We don't have enough experience to say for sure what the number was on those because we've not done it often enough. So these kinds of numbers, 10 on total carbon or alkalinity, a few percent on PCO2, pH in this range. These are all what I said we really need for the CCAN observing. Now, here I've just kind of gone through the seawater version, but I suspect they're going to scale a little bit the same way. As I said before, our experience is on this climate quality measurements. We have to kind of get away from that a little bit in our minds, and thinking how we do, I think, will be important. For these are the kinds of measured costs that we're currently seeing for these. Total carbons, probably, I think about, you know, they're all reasonable sized samples. Now that cost is for the cost per sample once you've already got a lab that's done 2,000 or 3,000 of these. It's not the cost for your first sample. That is meaningfully more. So I think that really what I've got here is just talking about, again, about the advantage and disadvantage of these techniques. And I'm going to build on this idea to make specific recommendations momentarily. But one of the keys, I think, is that we want systems that work reliably with limited degree of sophistication of the person operating it. And we're probably not quite there. For the infrared systems, certainly they seem to work quite reliably. They work on small samples. I don't know of that many labs that have really extensive experience with this, with less capable personnel, so that you can judge the failure modes as easily as you can judge how well it works. I know there's a number of labs that use this instrumentation that are very pleased with it, and we're just starting to try it here at Scripps. For pH, the ion-selective FETs seem very promising. Colorimetry can be very stable if you've got the dye purity handled. PCO2, there's this mental picture in many people that PCO2 is what's important to ocean acidification. Why? Because a lot of the laboratory experiments are trying to mimic this picture of a future atmosphere. There's a big meeting next month. The oceans in a high CO2 world. They mean PCO2. The mental picture is there of this link between this and ocean acidification. So probably one has to recognize that, even though my own opinion of that as a cost-benefit chemical analysis is a little disillusioned. So just to give you an idea of where we now stand, because it's sadly we don't stand where we would like to, I put together this table, which is looking at quality, availability of a measurement system. Level 0, there isn't a working, I'm not aware of a working system. Doesn't mean there isn't one, but I'm reasonably informed. Level 1, somebody's got one that they're probably still working on. It may be wonderful, like they told you, but that may only be on Tuesdays when the right person's using it. You don't know. When I make these jokes, they're based on experience in my own laboratory rather than snotty comments about anybody else. Level 2, they fixed it. But there's still only that one around. Level 3, a number of people said, oh, we need one of those too. And so they either got you to give them one, or they built their own based on talking to your graduate student, or based on what they thought that they heard when they talked to your graduate student. All these things vary, but I've used up an awful lot of levels without getting to where we'd really like to be, haven't I? Level 4, you can buy the instrument. Level 5, you can buy the instruments. It is reliable and it's supported. This is really what you would like. However, there aren't many level 5s on this picture. Mostly, this is still in development. For some of these, for discrete samples, we're getting there. For continuous pH and PCO2, and for discrete samples of alkalinity and total carbon. Really where the market has driven it thus far. There's a couple of companies will sell you instruments for total carbon and alkalinity, expressly for seawater. There are other ways to buy commercial instrumentation that you might be able to trick into working for you. pH, as I said, you can buy remote instrumentation, but otherwise you're kind of on your own for discrete samples, though there's a fair amount of experience with it. So my recommendations, if you said, what am I going to do? I'd say, if you're going to do total carbon, you want an infrared-based analyzer. Don't even go the other way. Why do I say that? Because although this is a lower precision measurement and thus a higher uncertainty. It's much easier and much quicker, and they seem to be reliable. Calibration is still an issue. If you're really trying to get the best quality data out of it, I'd say it's still not proven. But at reasonable quality, of the level we talked about, that's probably the way I'd go. For pH, I still think you want to go, if you're doing discrete samples, with a spectrophotometric approach. Because that way you don't have to worry so much about the calibration. Of course, you do have to worry about how you get hold of the pure dye. But that's the beauty. If you get hold of the pure dye, the calibration is built into the fact that it's a chemical with particular defined qualities, and behaves the same way every time. The Durafet you can buy, either directly from Honeywell, in which case you're kind of on your own on figuring out how best to use it and calibrate it. Also from Satlantic, where you're now one of a group of people saying, how should we use and calibrate this? It's not that there's a really clear way of doing it even then. Alkalinity, you can do it with an open cell titration, and you can sort of buy this commercially. You can build it from commercially available parts, those of you that want. PCO2, I threw a single thing up here, which I'm sure is contentious. I chose this particular company. I didn't even mention companies on the whole, because this system is actually designed to be simple and straightforward. On the other hand, that largely means that you don't, unless you're careful, you never know how well it's working. And that's always the problem with these things. So, proposed CCAN recommendations. Well, I think, realistically, we should be aiming to set up shore stations. Now, I say shore stations by virtue of the idea that they are easily accessible. If you actually lived in Southern California and had to go out briefly in a boat to a buoy, you could see from standing on the shore, that would almost count. If, on the other hand, it's a couple of 100 miles offshore and you need a ship to get anywhere near it, that probably doesn't count as a shore station. I think that measuring pH and PCO2 as well, and this is a problem, of course, you have to measure temperature and salinity to make any sense of pH and PCO2. If you don't have that information, you can't do the calculations I mentioned. So it's, without those, nothing. Now, I've got this term here, oxygen concentration. That's there because if there were any other chemical that was mentioned in any of the other discussions as being almost as important to have the information about, it was oxygen. And people's rationale for this varied from person to person and from need to need. One was simply to say, if you know the oxygen, then you can immediately get extra information about the processes that had caused those CO2 levels in that water sample. If CO2 is elevated and oxygen has gone down, chances are good it was a respiration effect. That was the kind of thinking about it. The other benefit for oxygen is there are continuous oxygen monitoring systems available. There's another piece that's been mentioned, and it's that, well, there's some great papers just coming out now from Dick Feely's lab pointing out that if you have oxygen and salinity and temperature, you can infer for significant parts of the ocean what the likely CO2 properties are. You probably should read those papers a little more carefully before going, Therefore, all I need to do is buy an oxygen meter. Because unfortunately, they require that you've previously done careful work to establish those relationships. There are limitations to how well you might reasonably expect such relationships to apply, and also they're quite demanding on how well you make the oxygen measurement. Nevertheless, I think that it's appropriate to recommend this for our shore stations, but I think that these stations really have to collect regular discrete samples that are analyzed. And once you put it in a bottle and send it away somewhere to be analyzed, you probably might just as well analyze alkalinity and total carbon. You could get away with doing other things. I'm open on that. The reason is they're intended to provide verification of the continuous measurements. At the moment, the continuous measurements largely look great until they don't. When I say until they don't, it's because suddenly they're giving numbers that are obviously wrong. This leads you, I fear, to suspect that there's this in-between part where they were giving numbers that were wrong but weren't obviously wrong. And you're not sure when the problem started. We don't have enough experience of running this equipment effectively in nearshore environments. Where they work really well is anywhere where you could guarantee there's nothing growing. They work less well if not much is growing, and not so well at all when lots is growing, because they get fouled. And we're still, I think, in the process of learning how to deal with that, how to know it's happened, how to recognize what the implications of that really are for the typical uncertainty of these data. So these discrete calibration samples are essential. Now, I mentioned the idea that maybe we should think as a bigger tent for this. And I feel that if it's not practical to have continuous measurements, and continuous measurements kind of get you in a bind of, first, you've got to have a place where you can put the equipment, preferably somewhere where nobody else is going to find it and decide that this is a desirable ornament for their lawn or eBay account. Then you have to keep it calibrated. You have to keep it clean. It's a substantial investment. There are already a number of shore stations run and whose data is being handled through the regional associations that we'll hear more from later today, but perhaps it's not such a big investment to get to that stage. That remains to be seen. So I think there's going to be other groups that are going to say, okay, but if we just had a time series of discrete samples, wouldn't we still be giving you some really useful data? And the answer is yes, I think. Because you'd have to analyze them for two parameters, and it would have to have the desired uncertainty, and you'd need to have some verification of this. Occasionally, there are going to be places that say, well, I've got one CO2 measurement. Well, not just one, but I regularly measure this one parameter. Wouldn't you like it? And you go, maybe. If it were verified, I don't think it's of such high priority. I think the restriction to saying that we can say what the aragonite saturation state is with the uncertainty I specified, and that we can say that what the complete CO2 system is with the implied uncertainty of that decision plays a role. So for our discussion, really, I've covered a lot of ground here. Number one is weather versus climate, that decision. I think that we need to clearly hear and understand the implications of emphasizing one or the other. My choice for weather reflects both the needs that I've heard articulated in CCAN meetings and what I recognize as a significant but bridgeable gap in where we now stand. And we'll talk more about what would be taken to bridge it tomorrow morning. Second, this relatively straightforward idea, though as there isn't a simple calculator you can do this with, a rather awkward concept of really getting the numbers you want, of saying, and we only have to do it this well. And the number that we had proposed both at our first meeting in Costa Mesa and then subsequently in discussions in a working group subcommittee that Burke Hales led was this number of around 0.2. And I've pointed out that that's actually not a very stringent number, which might lead you to go, whoa, well, is it good enough? Well, appropriate for biology. There are people in the audience that could either give me my standard OA answer, we don't know yet, or actually an answer. If that is okay, good. Otherwise, maybe we could refine it somewhat. If we refine it too much, we're back at climate scale measurements, and the resource implications of that are significant. Next is this potential dichotomy between a desire for continuous measurements and the potential benefits of a discrete time series. And obviously there's some discussion there as to what makes a time series useful. Once every now and then, possibly less so than once a month or once a week. But that again is an area for discussion. The role of oxygen in this. I've tried to take the founding acronym that I hope for CCAN, keep it simple. Why would we make it a little bit more complicated? Is it worthwhile? I've heard at previous meetings a number of arguments saying that yes, indeed, that particular measurement would be worthwhile. I'd like to hear that we are comfortable agreeing to that concept. So, having said that, I'd like to open the room up and the floor to discussion.
So this gets, I guess, to what would be a middle biological standard. And I'm speaking only of discrete measurements in my own ignorance. But every hospital emergency room, the first thing they do when you come in is measure your oxygen, your PCO2, and your pH. So there's instruments from radiometer, and there's old professors of mine who started companies, Jim Cameron and Capricorn. So, I mean, there is a standard. It may not be as good. It may be weather as opposed to climate, but at least you're not getting sued for malpractice. So there's some benchmarks there. There's some literature. There's some people who could guide you if you bought one of these instruments. And I just wondered if it's a disconnect between fields or those instruments aren't practical for experimentation. But we used to always measure blood PCO2 and pH and O2 and seawater and shoot them through biomedical instruments.
I think that's an interesting thought. My own picture on that, from thinking about it quite a while ago and not looking back at it more recently, had been that the PCO2 ranges being considered was so significantly different that the instruments were designed in a way that you'd have to modify them meaningfully before you could use them in this range. The pH part would probably work about the same as it does for blood.
So I just wanted to point out the statement that you made about assuming that the other parameter of your chosen pair was measured perfectly. And, you know, that's obviously not right, and it certainly, you know, if you applied both of those uncertainties, or, you know, the uncertainties to each parameter, then you come nowhere near 0.2. And so I think you have to take that into account, that assuming that you're only getting one of them wrong makes it look easy to get to 0.2 is not realistic.
Yeah, my comment on that, and I'm sorry I forgot to state it, was essentially that if they're a relatively simple combination, then if one of them is 1/3 of the number I gave there, it can be essentially considered perfect for the sake of this discussion. And 1/3 of some of those quite large numbers is still a quite achievable value.
So I was up in your lab during lunchtime, and Guy was showing us some of the really neat equipment. He showed us 2 of the 3 alkalinity titrators and said, well, how often do those agree with each other? He said, well, sometimes, but not all the time. And we said, well, how often when you measure total CO2 or PCO2, total alkalinity, pH, can you use the 2-parameter calculation to get the same number? And he said, not often. And there's discrete fudge factors, et cetera. And then we asked him, how many people in the world are trained as well as him to make these measurements? And he just smiled and said, I'm a very valuable employee. So given those sorts of comments, it was very entertaining. And we're going to, send us all off to different places on the California, Oregon, Washington, wherever coast to make these sorts of measurements and then try to relate them all together. Given the sorts of uncertainties in your very own lab with the uniquely qualified, skilled people you have, where does that leave us?
Needing to understand exactly what's being talked about. For instance, the degree of agreement in alkalinity, if our 2 instruments are 2 units out of 2,000, i.e. a 0.1% apart, we consider that a clear sign of a significant problem. For most people measuring alkalinity, that's still more than 3 times better than they typically measure it. So there are trade-offs here between all that valuable knowledge and exactly how relevant it is to our discussion. I think you have hit on a key point, which is that ensuring necessary training and understanding of what's required is there. But this is the real difficulty between the long and extensive experience in open ocean seawater measurements, which we have had, and people like Dick have had, and asking the question, which is, and how necessary is that level of uncertainty for what we're trying to achieve here? And I have my own prejudice, which I expressed, but it need not be everybody's, and I'm hoping this comes out in the discussion.
My turn? I'm not sure. Given that the number of us working in estuaries rather than open ocean environments, I was wondering if you could chime in, and maybe Burke could speak a little bit about this as well, about what of those parameters are preferred when you're not working at open ocean salinities.
My own comment on that would be that probably similar parameters would still be appropriate. The difficulty that we do have is understanding how to calibrate some of these measurements equally well over the range of salinities. And that's most strikingly true for pH. The others, perhaps much less so. Burke?
So, you know, I always say PCO2 and DIC, so that's what I was going to say. But the issues in estuarine settings are different for the two measurements, for the other two measurements, for pH and alkalinity. pH has complications in how the sensors respond to varying salinity and temperature, and the manufacturers typically, particularly the potentiometric sensor manufacturers, don't incorporate that at all. You know, the best example, or the worst example, I guess, is the YSI sensor, which tells you that they're giving you pH at 25C. But I'd be willing to bet that the correction, which they don't explain, is nothing more than a theoretical Nernstian slope correction, which probably isn't really giving you what you think it's giving you if you assume that that's the actual pH if that water sample were at 25. You know, so just the environmental conditions make pH measurements very difficult there. The alkalinity measurement approach, I think, is just as valid in fresh to brackish water as it is in open ocean. The issue is that the total alkalinity is less, probably, in the lower salinity systems, and the non-carbonate, non-borate alkalinity is probably greater. And that latter part is something that we just often don't know that much about. If it were only nutrients, and you had the ability to measure all the nutrients, that would be great. If it turns into reduced species or organic acids and bases, that complicates things quite a bit, and those complications, I think, become greater as the salinity gets lower.
Andrew, I was hoping that you could say a few words about how we as a community might go forward together to address these issues of both training and verification, that the training is work. That is, that if we were to have a CCAN program in which we're all dependent on the quality of the measurements that are measurable, that we have a series of steps that allow us to move in the direction that we know how good the community is doing. Can you add some comments to that effect?
I think that's an important issue, and yes, I do have some thoughts on this. That's in part what I was imagining in our debate for tomorrow morning of where we would go forward. I think we have to establish these things. Put simply, I think that what people would like to have is buy this and have it commercially available, use it this way and have written descriptions and or training courses, videos, whatever, and this is how you ascertain the quality. Again, written statements. Without that kind of infrastructure, written, it's hard. In my own laboratory, we have fragments of that written. Mostly, things are learned by a laying on of hands. The invaluable employee teaches somebody carefully how to do things and watches them first closely and then from a distance. Until they go, you know, they usually seem to do it right. But what I always say when we're training, we have this alkalinity is our best example of this, because we have, I think, 4 different systems for measuring alkalinity, some of which we send to sea, some of which we use in the lab, some of which other people use in our lab. And Guy can put that instrument together from the parts in about 2 hours. He can teach somebody to use it that afternoon. It takes about another 3 or 4 weeks before the person really starts to figure out when it wasn't working right. It takes about another 4 to 6 months before they're really in a position to, having figured out that it wasn't working right, to do something about it. Because it's this learning process whereby we don't have really good documentation that would help people. I think we could cut these times down, but you're never going to get them down to 0. It's so wonderful. The person comes in, they start making measurements. They're great. They go, oh, great, here, where are my samples? We go, well, up to you. How valuable are those samples? Because it really is this hard part of getting that trained. So I think that's a very important part, and I hope we're going to discuss it more extensively with concrete suggestions tomorrow.
Andrew, do you know if people, either on the global or on the national level, or institutes like yours, have you been in contact with the manufacturers of the instrumentation, kind of as with this as a goal, saying, you know, we're trying to ascertain this information everywhere on a standardized basis, and do we know if there are people working at Honeywell or elsewhere that are trying to devise a device that people would have a higher level of confidence in, or are we just hoping something like that comes along? Are we in touch with that industry at all?
Probably inadequately so. I think I should just point out that the difficulty for Honeywell is that this is a trivial part of a potential market. And so they have very little need to do that themselves. We're really trying to, the oceanographic community has been working with them in a variety of ways, but the particular level you're talking about, which is how do you use their equipment most effectively and make it simpler and more straightforward to use, they built it for a process control environment, mostly in industries. And it works perfectly well for that, and they know how to advise people on how to using it for that. This is a separate market, but no matter how many oysters you want to eat, there are not the level of interest that there is in factories that need to know their pH.
Do we know if anybody's been in touch with DOD with regard to deep sea research and on defense studies for this type of instrumentation?
There's a variety of bits and pieces. I think, you know, it's happening, but it's not happening as a commercially pushed thing. It's usually happening because there are people that are making it interest. One classic example of this that maybe Dick could talk to a little bit more, but there's an X Prize for ocean pH measurements. The goal, to measure pH correctly in a deep profile in the ocean. This kind of thing incentivizes groups to think about how they might do this, but at the moment, I'm not aware of numerous companies saying, oh, how could we win that $1 million? Because they're going to have to spend many times that to get to that point.
So I know that at a previous CCAN meeting, we had talked about intercalibration, and with the OCB group, there's also been talk about intercalibration exercises. I know this is obviously, I'm suggesting this prior to appropriate training, but I think this is still something that I hope that people are interested in.
So just to pile on Ian's comment, I mean, from what I hear you saying, Andrew, and what I hear from others is that there's a need for better instruments, sensors that are more easily used and more reliable. I recognize it's not going to make anybody a ton of money probably, but it seems that it could be a recommendation of CCAN and of other groups that have sort of the power to make recommendations, that instrument development be really a part of this. I mean, I think NSF would be receptive. NSF has, you know, a new program. They really want to spin out commercial development of new instruments and sensors. I think we need to take advantage of that, and we as a group could make that recommendation. It may not come in time for us, it may not be in a timely way for us, but it might come online 5 years from now. So just a suggestion.
So, certainly I think that almost every ocean acidification report I have read has articulated the need for improved technology. What's been less clear is a definition of what's really needed. The phrase is usually improved. My own opinion is at the level of measurement I put there, there are commercial instruments available. What we do not have are the descriptions on how to use them and make sure you are getting data of the quality that we think is necessary for the purposes I articulated here. So undoubtedly, new technology could help, but it's not what's in our way right now.
Two things. One is simple, one is not. And Ian, to your question about DOD, if I remember right, during the process, and Dick Feely, you may remember this in greater detail than I do. In the early days of implementing the FORAM Act, the DOD had people participating in some of the interagency discussions from Office of Naval Research, if I remember. And they concluded for their purposes that the consequences of acidification for attenuation of sonar were so trivial that they didn't care. So they lost interest. And you may have more detail on that, Dick, I'm not sure.
That's correct.
So they've got some data. I don't know whether it'll be useful to us. It didn't mean anything to them, so they're not pursuing it. To me, the tougher question, and this is really to both Dick and Andrew, I want to drill in a little bit on this distinction between climate quality versus weather quality and make sure I understand what we're saying when we say that. I think this means that if we're going to use weather quality data, it's valuable for resource management purposes, for biological investigations, for somebody who might be running a hatchery. It does not allow us to say from this data we can say anything about the phenomenon of ocean acidification and whether this data contributes to greater knowledge about the global anthropogenic load of CO2 driving change. Am I correct in that?
That's correct.
Okay.
I want. Oh. Hi, I just wanted to comment on some work that's going on with the Alliance for Coastal Technologies that I work with, and we're beginning, actually, in the development of protocols with Andrews and Burke's and a variety of other people's helps for at least laboratory-based, ecocosm-based testing of a variety of pH sensors. So this will address the issue of usability, reliability of the range of sensors that are out there commercially, and I'd agree with Andrew that it's not the actual sensing technology that's the limitation. It's, I think, more an issue of how reliable and available are reference materials. And earlier in the summer, we had spent some time with the crew talking about reference materials and the actual real issue of the difference in activity scales that are, or pH scales that are used for these certified reference materials and what the vendors are actually using. So as part of this ACT verification process, we're going to work with NIST and Andrew and everyone else and try to encourage the vendors of said equipments to utilize standardized reference materials all on the same scale so that I think part of these issues might disappear or become more understandable, and then back calibrating them between Andrew's lab, Bob Burns' lab at USF, using the dye techniques. So it hopefully is a user database that will help inform your selection of sensors down the road, reliability of those sensors over the long term. Are you saying then these reference materials would be manufactured by these Honeywell or somebody of these instrument manufacturers? Or I mean, I thought there's only one.
No, they're based on Andrew's system, but there's a postdoc at NIST who is being charged with, I think, redeveloping their standard system, so it's all on a similar pH scale.
Yeah, I would just echo that. I mean, I think our sensors are pretty
could be pretty good, but they're not, and it's just because of a lack of reference materials. You know,
Right,
I mean, I
and
think
the
we would be much
calibration
closer.
ability.
And I just wanted back to the weather and climate thing. You know, 0.2 difference in saturation state is not a big deal to me if it's reading 2.4 instead of 2.2. I'm going to fill the tank and spawn some larvae in that. But if it's a difference between 1.4 and 1.6, that's a difference between survival or death in my hatcheries. So I don't really feel like we're at which is the weather scale, right? I think we're a little bit above that. And on top of that is that we're not in blue water. You know, we're in estuaries, and there's also on top of this error, there's real departures from what you would expect in estuarine systems that add to the error. So if you're trying to get within 0.2, I think you also have to consider where we are in the estuarine system, and that a lot of these salinity-alkalinity relationships that hold up in the open ocean are not quite going to work so well, and that's introducing an extra level of error to our measurement. So we would like to be more precise than the weather level in our actual measurements to compensate for that. So.
Okay, we'll take a break now, and there's some drinks out there and probably the leftover granola bars from the morning for those that need added fortification. And we'll return back here in 30 minutes for the next part of our discussions. Thank you.